huh? Yeah. Okay, so good afternoon, everybody. I'm Matt Kubley, Professor of Electrical Engineering here at UAA. And it's my privilege and honor to introduce our speaker for today's engineering seminar, Brian O'Hare, who's coming to us from the Colorado School of Mines. I don't think it's an understatement to say that he's one of the world's leading authorities on fuel cell technology and implementation. So we're particularly lucky to have him here.
Thanks, Matt. All right, yeah, thanks for letting me visit. This has been awesome. I've known Professor Kublik since before he was Professor Kublik, I guess.
I may have taken a class.
We met in 1999, so 27 years ago now. But yes, it's wonderful to finally have the opportunity to come up here at the University of Anchorage and see what's going on. So I thought I would I'd give you a short talk here, focused mostly on just understanding what fuel cells are, and what some of their advantages and disadvantages are, how they operate, and then at the end, tell you a little bit about some applications of fuel cells and the kind of fuel cells that I do research on and why they might be interesting specifically for applications here in Alaska. So before I get started, quick show of hands, how many of you have heard of fuel cells? Yes, everyone's at least heard of them. How many of you know something about fuel cells? Maybe taking a class or just done a little bit of work, reading up in a book on them? Maybe about half. Okay. Well, that's fine. You don't have to know much about fuel cells. That's going to be the first half of the talk. So let's get started. So as Matt mentioned, I come from the Colorado School of Mines. Here's some pictures of our university campus and the environment around. You might recognize these mountains, the Maroon Bells near Aspen. Matt and I actually did a 3-day backcountry trip through those in the dead of winter up to Conundrum Hot Springs and then kind of all the way around. Quite an adventure. It snowed a bunch on us. Made getting back out a little bit challenging, but super fun. So my research involves the Colorado Fuel Cell Center. I work on fuel cells, and we actually have one of the nation's largest research laboratories devoted to fuel cell science and technology. We teach a class, which Matt took years ago, still teaching it every year. We typically get over 60 students enrolled in that class, so it's one of the largest fuel cell specific classes in the US. We do both fundamental kind of research, developing new materials, trying to understand fuel cells and how they work at like the atomic and chemical level, but also applications and scale up with a lot of commercialization partners in industry. So if you ever have a chance to come down to Colorado and you're in the Golden area, please come visit us. We do have skiing in mountains this year, not so much. The snow hasn't been very good, but yeah, there's some good stuff to be had. That's Dead Dog Couloir, Torrey's Peak, less than a 40-minute drive from Golden. Matt and I did that. Actually, it was in March, I think, around spring break time. I don't know, 20-some years ago. And this is from that. I think that's also from Dead Dog. Some pictures from the Aspen tour. Yeah, good times. Fun stuff to be had down there. All right, so let's talk about fuel cells. So what is a fuel cell? A fuel cell is a way of taking chemical energy, usually gases, and converting those directly into electricity through the magic of electrochemistry. So instead of burning the fuel like we would in a combustion engine and then eventually turn that into electricity, you can do it directly. And this schematic is kind of what the very first fuel cell developed by Andrew Grove more than 150 years ago now, what it might have looked like when he was doing the experiments in his lab. So imagine you have a glass beaker and it's just filled with sulfuric acid. And then you take two wires. They should be catalytically active. So if you've got the money, maybe you want to make them out of platinum. And you dip those two wires into the sulfuric acid. And then you take two little tubes and you bubble either air or pure oxygen across one of the wires. And then some type of fuel, hydrogen works best, but it's not the only fuel you can use. And you bubble that across the other wire. And the hydrogen is going to, catalyzed by the wire, by the platinum in the wire, is going to split apart into protons, which, because this is sulfuric acid, protons will happily swim across to the other wire, and then electrons. And the electrons get liberated and sent through the external circuit, and that's how we get electricity from our fuel cell device. And then those electrons come back down into the other wire, recombine with the protons and oxygen. And so when you have protons, oxygen, and the electrons to balance the charge, you make water. So essentially you're taking hydrogen and oxygen, turning them into water and electricity, but you're doing it without combusting the hydrogen, without burning it. So that has the opportunity to make this very, very efficient. So this is what the very first fuel cell might have looked like. We can think of it as a gas battery, basically. But this wouldn't be a very good fuel cell. So just kind of thinking about basic physical principles, simple chemistry. If you were to try and design a better fuel cell than Grove did 150 years ago, what are some things you might do to modify this, make it better? Draw suggestions. This is your first day of lab. Professors are allowed to answer too if they want.
Increase the surface area.
Bingo, right? So instead of like just plain old wires, if we make plates, have much more catalytic surface area, absolutely, that's gonna basically be a reaction rate. The amount of electricity we can generate is gonna scale with the area. So if we can make plate-like electrodes, that's gonna help a lot. What else might we wanna do? About this distance between the two wires. Yeah, bingo, right? We wanna make that as small as possible, right? So decrease that distance, bring those closer and closer together. What's the problem though, as we start to bring those closer and closer together? Especially if we're just bubbling gases and this is a liquid.
Cross
Yes,
contamination.
absolutely, right? So you're gonna get crosstalk. What if some of the oxygen sees the hydrogen and they both meet on one of the wires? That platinum catalyst is gonna catalyze a combustion reaction and you just have yourself an explosion. So you wanna bring those really close together, but you can't let the gases talk to each other. So we can think about maybe going from a liquid electrolyte to a solid electrolyte. Okay, so those are exactly the type of design principles that are used in modern fuel cells today. So this is what a modern fuel cell looks like, right? So instead of those wire electrodes, we use big plate electrodes. And instead of aqueous sulfuric acid as our electrolyte, we use this thin polymer or ceramic membrane, which serves the same purpose. So it's electrically insulating, but it's ionically conductive. And because it's solid, that allows us to make it super, super thin and bring these two electrodes as close together as possible. But now the gases still can't permeate through that solid membrane, right? So most of the problem's solved. All right. So why are we excited about fuel cells? They offer some interesting advantages. We don't go through combustion, so we don't go through the heat bottleneck, the Carnot cycle efficiency. That means we can be more efficient in producing electricity. We're not burning anything, so there's no particulates, there's no NOx or SOx or pollutants that are generated. These devices are silent, so there's no moving parts. There may be some moving parts associated with the system, we'll talk about that later, but the device itself, the fuel cell itself, doesn't have any moving parts. So the military is interested in them because they're quiet power conversion devices. The fuel cells are remarkably scalable. So we've made fuel cells that fit on like an integrated circuit chip that you can use for like remote sensing applications. And then there's also fuel cells that are big enough to make an entire power plant, the megawatt scale. So there's like, you can't really scale combustion engines to fit on a micro chip, right? So there's not many other power technologies that scale from the microwatt to the megawatt. Now there's also one interesting advantage, and that's I think would be particularly interesting if Alaska wanted to pursue larger scale fuel cell applications. And that is essentially fuel cells give you CO2 sequestration for free. Okay. So I want to talk a little bit about this because this is hardly ever mentioned in the fuel cell field, but I think it's a really interesting advantage. So let's think about how we mostly make electric power today, which is in a conventional fossil fuel power plant. This could be coal, could be natural gas, but basically whatever you have, whether it's natural gas or coal, you feed it into some type of a combustion chamber, you mix it with the air, you do combustion, and as a result, you're going to have a single outlet and a single exhaust of your combustion products. And so that exhaust contains the CO2, which we might want to separate, and everything else. And part of the problem with doing CO2 sequestration is how do you do that separation? And so if we wanted to sequester the CO2 from a conventional power plant, for every 2 conventional power plants that we want to sequester CO2 from, we'd have to build a third one just to provide enough energy to do that separations process. All right, so that's kind of makes it non-economic. Now let's think about how a fuel cell would do this. So same idea, we're going to use methane or coal as our, whatever we want to use as our fuel, just like a conventional power plant, and air. But now This is a membrane device, right? So you have the solid membrane separating two electrodes. And so you have two gas compartments. And those two gases never mix. They always stay on either side of the fuel cell. So the fuel always hangs out here, the oxygen always hangs out here, and you get two separate outlets. The kind of reacted fuel, which is mostly just CO2 with some water, and then the cathode exhaust, which has everything else. The water is really easy to separate. All you do is cool the stream down, which you have to do anyway to recover heat. So you cool this down below 100 degrees, the water crashes out as a liquid, and you basically have pure CO2. You can sequester, you can use it for useful purposes, make a beer, whatever you want to do. So that's a huge advantage of fuel cells over conventional power plants. Another interesting advantage of fuel cells that's just kind of in the last 5 years or so taken off is what's known as reversible fuel cells. So if you take a fuel cell, so we're talking about right here, here's our fuel cell, we're supplying hydrogen to one side from a tank, air to the other side, we make water. All right, so that's a fuel cell, we're making electricity. What if we have renewable power on the grid and it's a sunny summer in Alaska, we've got tons of renewable power that we don't know what to do with. All right, so once we've already powered all our homes and our buildings and everything else, we still have excess renewables. We can use that to reverse our fuel cells, the same exact device. Now we're just going to send electricity into it and run it backwards. When we run it backwards, we feed it water and it'll split the water. It's what's called electrolysis and make hydrogen. So we use that extra renewable energy in the summer that's basically free to make hydrogen, and then we can store it. Here you've got a lot of, where you've pumped the oil and gas out of the ground, you've got a lot of caverns that are suitable for geologic storage. So you could pump all that hydrogen down underground for almost free. And then in the winter when it's cold and dark and you need that electricity, you simply run your device again in fuel cell mode and you pull that hydrogen that you've stored all summer out of the ground and you make electricity. And so you can do this back and forth, just like a battery. But essentially this is a giant gas battery with a storage that's much, much larger and more extended than it would be for a battery system, right? Because we can take advantage of geologic storage to store all that hydrogen. In addition, if you look at the relative size of a fuel cell versus a battery, for the same amount of backup power, you can do it in a fuel cell that's much smaller than the equivalent battery. So space is also a constraint. Then again, fuel cells can win. Now there's two main types of fuel cell technology that are being commercialized today, and they both have very distinct characteristics and very distinct kind of advantages and disadvantages. So the two main types are what are known as polymer-based fuel cells at the top, and then solid oxide or ceramic-based fuel cells on the bottom. So the polymer fuel cells work with that electrolyte. Remember we said it's important to make that electrolyte as thin as possible. We've got to make it out of a solid so the gases can't cross. So for the polymer electrolyte fuel cells, that electrolyte is a polymer. So if you ever have leftovers and you put saran wrap over the leftovers before you put them in the fridge, that polymer membrane that's inside of those fuel cells is basically like saran wrap. It's a super fancy saran wrap that conducts protons, but effectively, if I were to give you a piece of this, you wouldn't really be able to tell the difference between that and saran wrap. So that's kind of what it feels and looks like. So those run at basically room temperature, or a little bit above room temperature. They're pretty high power density, so a small little fuel cell device can make a lot of power, but they're not super efficient. They're typically 40 to 60% efficient. That's better than an engine, but it's nothing to write home about. The solid oxide fuel cells, these are the ones based on ceramic technology. So think toilet bowls, coffee cups, but these are super, super thin, again, plates of ceramic. And it's a special kind of ceramic that's an ion conductor. So to get the ceramic to conduct ions, you have to heat it up to kind of glowing red hot temperatures. And then it works. So it doesn't work at room temperature. So these kind of devices really are only good if you're going to kind of turn it on and leave it on, because you're not going to like heat it up and cool it down and heat it up and cool it down all the time. It's not very efficient and it would take a lot of time. So these kind of fuel cells are better for this base load kind of long-term continuous operation, but they're much, much more efficient. So solid oxide fuel cells, we can get 70 to 80% efficient. If you want the heat also, which in Alaska, oftentimes you do, right? So we have what's called combined heat and power. We can have the fuel cell produce electricity for the building, but also produce some of the heat for the building. In that case, the combined heat and power efficiency can be 90% plus. So that's super awesome. All right. So in either case, I want to show you peer inside of a fuel cell and see how it works. Okay. So this is like a cross-sectional view if you're to cut open a single fuel cell and look inside of it. So we're kind of looking at it from the side. So this is a side view of that, the two electrodes that we talked about, and then that thin membrane, whether it's a polymer or ceramic in between. And then we have two compartments, and we have some type of like a manifold that seals the gases and distributes them evenly across the surface of the fuel cell. So in the third dimension coming out of this is like a big old plate, right? And so these gold things, those are the manifolds, and they kind of, usually there's channels etched into them, and that's distributing the gases all across that two-dimensional area of the fuel cell. So you have one for the hydrogen side, you have one for the oxygen side. In fuel cell mode, just like in a battery, they're basically a positive and negative sides of the fuel cell, like you have plus and minus on a battery. We call those the anode and the cathode. And so hydrogen goes in on one side, oxygen goes on the other side, water comes out. If there's any hydrogen that doesn't get reacted, it'll come out here. You can recycle it back in, so you never waste or lose any of the hydrogen. And the electrons, again, are collected. Usually these manifolds are electrically conductive. So not only do they provide like the sealing and the route distribution of gases, they also provide the electrical contact. And so just like the battery, you have your two little terminals that you hook up, right? These would be where you would attach your wires to collect the electricity that's generated. Now, all of the magic, all of the chemistry in a fuel cell happens right here at the interface between the electrolyte and one of the electrodes. You can pick either one. Let's take a look at that interface right there. I've rotated this picture 90 degrees. So the electrolyte now is on the left. That was this. And the protons are swimming across that electrolyte, right? So they're coming in from the left-hand side. The electrode is on the right. And for a polymer fuel cell, that electrode is usually like a carbon paper or carbon cloth. So it's like graphite fibers that are woven together. And so it's somewhat porous. And that allows oxygen from the air to kind of diffuse through that porous electrode structure. And then right at the interface between that porous electrode and the electrolyte, we put a thin layer of our catalyst. And typically for a polymer fuel cell, that catalyst is these super fine carbon powder particles. And decorated on the surface of those carbon particles are even smaller, little tiny platinum catalyst particles. Now we could just put a whole bunch of platinum right there and it would work even better, but that would be super, super expensive. So the name of the game here is to try and thrift the platinum and use as little as possible, get the biggest bang for your buck. So this kind of structure works really well because we basically have just a tiny little bit of platinum, but it's all used very, very efficiently. Okay, so protons come in, oxygen from the air comes in, and they all have to meet. Let's see if this works. So they all have to meet on a platinum catalyst particle in order for this reaction to occur. Because you see, it needs oxygen gas, it needs the protons that are being supplied by the electrolyte, and it needs the electrons that are coming in. And when all three of those species meet on a catalyst particle, we call that a triple phase boundary. So you have the electrolyte phase that's supplying the protons, you have pores, gas phase, that's supplying the oxygen, and then you have electrons in the catalyst, right, that's supplying the electrons here. So you need all three phases, so we call it a triple phase boundary. So every time you get one of these little triple phase boundaries, you can have the reaction. And so when we try and design this interface for fuel cells, it's almost as much of a black art as it is a science. What we're trying to do is maximize the number of these triple phase boundaries. If you do this well, you can get an effective kind of surface area for catalysis that's as much as 1,000, 2,000, 3,000 times larger than the geometric area, like the projected area, right? So if you had a 1 square centimeter fuel cell like this, it could actually have like 1,000 square centimeters effective catalyst surface area there at that interface.
So just for reference, how thick is this section that has the platinum?
Yeah, great question. Typically this thin catalyst layer is on the order of microns, 5 to 30 microns.
Okay.
Yeah. The carbon electrode is going to be 300 microns or so, half a millimeter at the most. The electrolyte membrane is typically nowadays like 25 microns, 25 to 50 for the polymers. For the ceramics, we can actually get down, and we need to because ceramics are less conductive, down below 10 microns nowadays, the state of the art. So those layers are all super thin. Yeah, great question.
Another question, so I assume the efficiency degrades over time, and if so, is it have to do with like those platinum particles?
That's one of the big sources of loss over time. Yeah. And so some of those platinum particles will move around, they'll get dislodged. You have coarsening, where like the platinum particles will actually coarsen. So you have fewer of them, but they're bigger. So you're losing effective surface area.
How much time?
It depends on, yeah, so the very best fuel cells, we'll talk about this a little bit later when we get to applications. Very best fuel cells today can go 10,000 hours, 20,000 hours, just good. But if you're running it constantly, that only gets you maybe 2 years, right? So that's a big Achilles heel right now. And one of the major things we need to do to improve fuel cells, make them run longer. So, all right, so if you use a powerful microscope, like a transmission electron microscope that can see almost at the atomic level, you can zoom in on one of those carbon platinum catalyst structures. And so here is a TEM image. I don't know how well you can see this with the lights, but that scale bar there is 2 nanometers. So an atom is like 0.2 nanometers. So that's about 20 atoms. That scale bar is about 20 atoms. And in fact, these little tiny darker dots, those are the platinum nanoparticles. And they're sitting on top of this kind of bigger structure. That's the particle of carbon. And you can even start to make out the lattice, the individual crystal lattice fringes of the platinum atoms in those particles. So we're almost zooming into the atomic level. All right, so this is what an actual PEM fuel cell device looks like. So I didn't bring any all the way up here through the airport. In class, I would have show and tell, so apologize for that. But if you were to hold one in your hand, this is what it looked like. So this is that kind of saran wrap type polymer. And then here are these woven carbon cloth or carbon paper electrodes. Now, if we were to flip it over, there'd be a similar electrode on the other side. And you can't see the catalyst layer, but it's basically, right, it's directly under this. If you were to peel off this carbon electrode, you'd see that catalyst layer. It's just like a black coating. So that was for polymer fuel cells. We'll talk a little bit now about the ceramic fuel cells. So now this is more of a 3-dimensional cross-sectional view through a typical ceramic fuel cell structure. So now you get a better sense of what these manifolds that I was talking about look like. They have these channels, right, for distributing the gases across the 2-dimensional surface area of our fuel cell. So now this is the heart of the fuel cell. We call this that membrane electrode assembly. The electrolyte is this dense red layer. That's a dense, thin ceramic on the order of 10 microns. The cathode electrode is also pretty thin, typically 30 microns. So these 2 layers combined are like 40 microns. You can barely see it with the naked eye. What's one problem with ceramics? Are they like super robust and can you bend them? Or are they fragile and break? Right, they're fragile and break, right? And so if you want these layers to be as thin as possible, but you're fighting like the mechanical properties of ceramics, right? So you have to pick at least one of the 3 layers of the ceramic fuel cell to be fat and strong to provide like mechanical support for the whole cell. And so for various reasons, we almost always choose the fuel electrode, the anode, to be the thick one. So we basically make this thick anode, which is half a millimeter, 500 microns, maybe even a millimeter thick. And usually make them in square or disc kind of button cell shapes. And then we deposit various ways. We deposit the other 2 super thin layers on top. So the anode provides the mechanical support. The anode's also the one that needs to do all the fancy chemistry, especially if you're going to supply methane or coal or more complicated fuels, because those fuels have to be reformed. And you can do this internally in the pore spaces of the anode. So the fuel comes in and it gets reformed. And because this is nice and thick, we have plenty of time, residence time, for all those fuel species to get reformed, so that by the time the fuel gets here close to the electrolyte, it's mostly already decomposed into hydrogen, right? And so it's really the hydrogen then that reacts, just like it did in the other kind of fuel cell. Okay. So this is what a typical ceramic fuel cell would look like. So if I were to bring these in, again, you can make them any size, from the size of like a US quarter, and the biggest ones I've seen are about a meter by meter. Kind of, that gives you the scale. So The green part here is the main ceramic, and then the thin black, that's that electrode, again, that porous electrode that we've painted or sprayed on top. Okay, so let's talk a little bit about how you quantify the performance of a fuel cell, right? So we want a fuel cell to produce as much power as possible. And so the first thing you do in the lab after you make a fuel cell is you'll measure its JV curve or IV curve. So this is the voltage output of the fuel cell on the y-axis as a function of how much current, how much electricity it's producing. And we normalize by the area of the fuel cell so you can compare apples to apples. Of course, a bigger fuel cell is going to produce more current, right? So to compare my little small fuel cell with somebody else's big fuel cell, you just divide by the area of the fuel cell. So you have a more fair apples to apples comparison. So this is current density. So amount of electricity produced per unit area of fuel cell. Okay, so when you turn on your fuel cell at open circuit, before you start demanding any electricity from it, you get about 1 volt. That's nice. The problem is, as soon as you start asking for electricity, the voltage of the fuel cell drops. You know, there's no such thing as a free lunch, right? And so this represents efficiency losses. And so as you demand more and more electricity from your fuel cell, you can get more current out, but you're going to sacrifice some of the voltage. And you typically, for reasons that we don't really have time to get into here, but you typically see a shape to the to the current performance curve, something like this S. So you get an initial decline in voltage, sharp decline in voltage. Then you get into a linear region. This is mostly obeying Ohm's law of equals IR. You're seeing the resistance losses of the fuel cell. And then finally, at really, really high current densities, the fuel cell's output just falls off. It drops like a rock. Out here, the problem is fluid dynamics. Basically, you can't supply the fuel to these reaction centers fast enough compared to how quickly they're being consumed. And so you reach just a fundamental limit to gas transport. Okay, so this is voltage versus current, but we might be more interested in the power that our fuel cell is producing. So how would you take voltage and current and calculate power? Most of your double E's, so I hope this is a really easy question. You multiply, right? So we can pick any point on this curve and take the voltage and the power, or voltage and the current at that particular spot, multiply it together, and we'll get the power, right? So when we first turn it on, we have no current, but high voltage. What's the power? No current. Current is 0. So what's the power?
0.
0, right? Now let's turn it on, right? We get out here. The voltage is down at maybe 0.7, but now we have a decent amount of current. You multiply those two numbers together, you're going to get something. It's going to go up. But then now we get to really high current, and eventually if I continue this curve, it's going to plummet down here. And at some point, we're going to have a lot of current. We're going to be at like 1.5, 1.6 amps per square centimeter, but we'll have 0 voltage. So again, what would the power be? 0, right? So the power curve is going to kind of start at 0, it's going to go up, and it's going to come back down. And so this is what we typically see. And it's kind of like a parabola, but it's not a perfect parabola because the IV curve was not a perfect line, right? Okay. So this power curve will tell you, like, per unit area of fuel cell, how much power could you produce. And you might want to operate here at the power density maximum if you care most about power. But if you care most about efficiency, you'll typically operate in this region, kind of somewhere on the upward slope of the power density curve, but not all the way at the top. And that's because you'll operate more efficiently here. So there's always trade-offs. What do you care most about? Efficiency, power. So this is, you can kind of figure that out for your specific application, how you design your fuel cell. Okay, so we were talking about what are some of the problems with fuel cells. You ever seen these spider charts before? The Department of Energy loves these spider charts. So you plot basic like performance metrics that you care about for a particular technology. What we want, our goal, which is at the outer edge of the kind of spider web, right? So this is the kind of efficiency we'd like to reach, power density, cost, how long we want it to last, right? And then the blue is the current state of the art. This is for a particular type of fuel cell, right? And so you can see that how the gap between the blue spider web and the outer spider web, how close or how far we are from the targets. So that I circled the two that we're kind of the furthest away from, so durability, how long they last, and cost. Right now they're really expensive and they don't last very long. So nobody's going to buy a technology that's expensive and then doesn't last as long as the incumbent technology that's already cheaper. So those are things we really still have to work with. Okay, so that brings us to fuel cell technology. So first, how do you make these things? So if you're to come down to Colorado and visit the fuel cell center, you can actually see how fuel cells are made in the lab. The process is very different for the polymer fuel cells, the low temperature fuel cells versus the ceramic high temperature fuel cells. If you've ever made like a t-shirt using a screen printing process, or if you've ever seen like newspaper or roll to roll like newspaper press, you basically use those same technologies to make a polymer fuel cell. It's like making newspaper or making t-shirts. The only difference compared to a newspaper or a t-shirt is the ink. This will be the most expensive ink you've ever used. And that's because the ink has all this platinum in it, right? So you wouldn't use this ink on your t-shirt. All right, so PEM fuel cells, polymer fuel cells, the fabrication process, super cheap, super easy. The materials that go into it, like this ink and this polymer membrane, those are very, very expensive. Okay. Ceramic fuel cells is kind of the opposite. So the materials, the raw powders that you use are super cheap. They're basically like rocks. Ceramics tend to be pretty cheap. What's expensive is the fabrication process. It's tons and tons of steps. Many of these steps require super high temperatures, and that's expensive, like firing at 1550 degrees Celsius, that gets pricey. So it's the fabrication process that's the Achilles heel for the high temperature fuel cells. So again, here's a few more examples of the polymer and solid oxide. The nice thing about the solid oxide fuel cells, right, we can form ceramics into pretty much any shape you want, right? You can make a coffee cup or a toilet bowl out of the ceramic. And so you could make, if you wanted to, I suppose, you can make a toilet bowl shaped fuel cell, ceramic fuel cell, if you wanted to. It probably wouldn't be very good, but you could do it. So the two most common architectures for solid oxide fuel cells are these planar button cells or tubular cells. Tubular cells have some mechanical advantages. They tend to be stronger, everything else being equal compared to like a flat plate, right? And we usually do, here you see these are all square, but for the ceramic ones, we tend to make them circular. Again, thinking about strength and stuff, does anyone have an idea why we might do circles instead of squares?
So the corners don't break off.
Bingo, right? So stress concentration factor, right? So these in a ceramic, the corners would be, yeah, the failure points, stress concentration, right? So if you make it a circle, you don't have any corners, you minimize stress concentration.
And you hook terminals to them.
What's that?
How do you hook terminals to them?
Great, here we go, yeah. So just like with batteries, a single battery, like an alkaline battery, AA battery, AAA battery, right, about 1.5 volts. Your flashlight needs 8 volts or something, right? So what do? You take a bunch of batteries and you stack them, right? Put them into your flashlight, back to back, you stack them up. Same idea with fuel cells. So we usually don't just operate a single fuel cell, we operate a stack of fuel cells, right? So all these plates, all these thin fuel cells with manifolds in between them. And so these manifolds would connect the plus of one fuel cell with the minus of the next one. And you just continue to repeat and alternate, plus, minus, just like you're stacking up batteries. And so with the stack strategy, we can easily build up voltage to tens, hundreds, thousands of volts, depending on how many cells you stack in series. And then the packaging on the end plates, you have thicker end plates, which have these inlet and outlet terminals for supplying the gas. And those then connect to these smaller pass-throughs that are in each of the repeat units. So that's how we connect everything, wire everything up both electrically and fluidly, right? So both the gases and the electrical pathways have to be designed to kind of connect everything cleverly together here. That's called stacking. So that's a whole nother aspect of fuel cell technology. It's how you design these stacks to connect a whole bunch of fuel cells together, right? And in the battery community, that's solved, right? Here's our competition. These things super robust, super durable. You drop a battery on the floor and you don't worry about it breaking, right? So somehow we need to figure out how to package fuel cells so they're just as kind of dummy-proof, the Army says, as batteries. Once we can make fuel cells like this, then the Army can adopt them for soldiers. Okay. Now, fuel cell itself, super elegant, no moving parts, silent, efficient. The bad news, well, I guess for you it's good news. It's primarily double E's and MECs. A fuel cell by itself doesn't really do you much good. You need to have a fuel cell system. to get useful long-term power. So what's a fuel cell system? Well, it combines the fuel cell itself with all the other things that you need to do to run it. Like you may need a blower to force the air into the fuel cell stack. You need a tank to store the fuel and then some kind of pump or another type of distributor, right? If this is a liquid fuel or a gaseous fuel, again, you need some way of forcing that fuel and metering it into the stack. In this case, if we're starting with a liquid fuel and we need to turn it into a gas, you might need a vaporizer. You need a combustor here. If we're using hydrocarbon fuels, you need a recuperator to kind of capture the waste heat. You need a control system, which is not shown here, power conditioning, etc. Here's the actual stack again. So this is the stack part. When you add, so here's the stack. When you add all those other pieces, including the tank for your fuel, the whole entire device is way bigger than just the fuel cell itself. And the total cost is way higher than just the cost of the fuel cell itself. So the fuel cell part itself may only take up about 25% of the volume of the fuel cell system, and it may represent about 30% of the cost. So all these other components basically actually dominate the cost. And this is an opportunity for WEs and MECs, right, to think about how we do that kind of system design to bring down the cost and make these fuel cell systems simpler and more efficient. So this is a tiny little fuel cell. This was actually a DARPA project, military project, to design a fuel cell that a soldier could carry on their backpack for some type of remote forward operating type mission. So that's like 100 watts, let's say. But then here's a fuel cell. This is a power plant scale fuel cell. You see a person for scale. So here, this is the fuel cell. It's in this pressure vessel. And then again, all this other crap is basically the system stuff, all the WE stuff. Right, so again, the whole system much bigger and much more expensive than just the fuel cell part itself. Okay, applications. So I like to divide potential applications for fuel cells into 3 primary categories. So you have portable, like that soldier application we talked about, or maybe a fuel cell powered laptop. You have stationary. So again, think microgrids, combined heat and power. You could even have your own fuel cell in the basement that would replace your water heater. You got a water heater that runs on natural gas, replace it with a fuel cell. Fuel cell will take that same natural gas that your water heater used. It'll still heat the water for your house, and you'll get extra free electricity on top of that. So kind of if you're living in a place like in Japan, where natural gas is super expensive, these fuel cell stationary units are actually taking off. They make financial sense already in Japan. So there's hundreds of thousands of these in residential households in Japan, especially northern Japan, Hokkaido. Finally, vehicular. So George Bush, I don't know how many of you are old enough to remember his I don't know, one of his State of the Union speeches 20 some years ago, saying how we'd all be driving fuel cell cars. That hasn't happened. And that's because this is a really daunting problem. This is actually probably the last application space for fuel cells, and already batteries are much better for vehicles. So maybe for semi-trucks, long distance trucking, that's maybe where fuel cells are going to make sense. But otherwise, I don't really see much potential for vehicular applications for fuel cells. I see the biggest potential here in the stationary application. And the biggest challenge is the fuel problem. If you're going to run in a stationary application to kind of be part of a microgrid, you're not going to run on hydrogen. Nobody has hydrogen in their microgrid, right? They probably have natural gas. And so making sure that our fuel cell can run on natural gas is critical. Okay. So this brings us to Alaska and fuel cells for remote and backup power, which falls under that stationary application. So if we look at the competing technologies, batteries, diesel, microturbines, those are kind of what are used today in microgrids or in backup power applications. It's a huge market, over a terawatt of power per year. Here's how they do it in India, and I think maybe in some of the northern communities here. So these big old nasty, noisy diesel generators. Here is in Australia, where they use giant banks of lead acid batteries to power a village. Now, would you like these as your remote power, or would you like one of these? This is a Bloombox energy server. If you walked by one of these, you wouldn't even notice it. It would look just like any nondescript utility box that's outside of everybody's building or house, right? About the same size, relatively quiet. It might just emit a little bit of a hum, If you put your hand on it, it might be slightly warm, but otherwise you wouldn't even know that that you're standing next to a massive power plant that's producing hundreds of kilowatts of power. So because these are so quiet, this solves the whole NIMBY problem, not in my backyard, right? So let's talk a little bit about batteries. So you probably heard of the Tesla Powerwall, right? So you can get one of these, put it in your garage. For scale here, I don't know, it's like maybe 2 feet by 4 feet or something like that, to give you an idea about the size of this whiteboard, and maybe 2.5 feet across, right? Something like that, right? Single one of those. You take 61 of those and you put them together, that would be the equivalent of one of those balloon boxes that I was talking about, right? So now you can see the advantage, the power density advantage of fuel cells. Cell phone towers. This is actually where fuel cells are used today, including in Alaska. So you have these remote cell phone towers. They might be hooked up to the grid, but you still need to have a backup. If the grid goes down, we even need communication even more in those type of emergency situations. So all cell phone tower installations are required to have a backup. And this is where fuel cells are often used. And so here's one of the companies that does fuel cells for cell phone backup power. So these are just all over the Pacific Northwest and in Alaska, mostly in the western side of the US.
So, are they used for backup because of the limited lifespan, like the 5,000 hours, you don't want to just burn through them?
Yes, and they're also used for backup because if you were to do a battery, so they're seldom used, right? Like how often do you have, well, more and more nowadays in Colorado, we're getting a lot of outages. But how often do you have an outage? Well, if you had a battery, right, you would kind of say the next outage is going to be 4 months from now. So that battery is going to slowly discharge over time. You're going to have to recharge it so that it's always ready. So you're constantly topping off that battery, and that's bad for the battery. And if it's just sitting there for 4 months and not getting fully discharged, maybe that battery's not gonna, it doesn't have a good life, and it won't be very effective, and it'll quickly fade in terms of its performance. Whereas a fuel cell doesn't care if it's off for 4 months, then you turn it on for backup power.
But you have to have a source of
Correct.
fuel.
Correct. So a lot of these have a propane. So they just have propane, and that tank of propane will just sit there forever, right? It's not going to discharge the way a battery would self-discharge. They've also done this for road intersections with rail, right? So you have a train crossing a road, right? And you have the things that come down that prevent cars from driving and getting smashed by a car, by the train. So those again are tied into the grid, but again, just like the cell phone towers, required to have a backup, right? Because if that was to fail and a train comes by, you still want the safety. And so again, fuel cells and batteries were often used. They had a problem with the batteries, people would steal them, right? Because these train crossings are in more urban areas, easily accessible. The cell phone application is way up in some wilderness, so the theft isn't as big of a problem. But for the rail application, theft was a huge problem. So a lot of them went from batteries to fuel cells. Nobody knew what a fuel cell was. Nobody wanted to steal it. It's not going to be very useful on its own without, taking the whole system. So that put down a lot of the theft problems. Now, people sometimes stealing the propane tank, so that becomes an issue. So they've disguised the propane tanks and gone to different kind of propane storage. But yeah, so that's.
So you said there's lots of them. What's the market penetration?
Oh gosh, I had a slide that I took out here. I want to say we're at hundreds of megawatts worth of fuel cells in commercial application.
Generally speaking.
Yeah, so these are relatively low power, so their contribution to the total megawatt market isn't very large, but these are very high value application. But yeah, I couldn't tell you the exact numbers without looking.
And how does the cost compare to the installed cost compared to just a backup generator?
Yeah, 2 to 3x probably more expensive. Yeah. So it's so if you have an application, so another reason that they like the fuel cell is less maintenance. And so if you have to pay somebody to go out every 3 months and check on stuff and maintain stuff, that ends up being a lot more expensive than the initial capital upfront purchase, right? And so if you go to a technology solution that doesn't require labor to come and check on it all the time, you save money, and even after just a couple of years, you're in the green.
Yeah, but we have But we send people out to take care of the rest of the equipment regularly anyway.
I see, yeah, so maybe it doesn't really save you much in that case. Yeah. Okay, so microgrids, and actually this is a paper that I found from Erin, when she was still at NLR, NREL, now called NLR, down in Colorado. Yeah. So the scientist here, she until very recently was in charge of, where is it called? I thought I had it somewhere. Basically, yeah. So the U.S. Department of Energy Arctic Field Office up in Fairbanks. But I understand she's recently moved on.
Yep.
Before that, she was a scientist at NREL, the National Renewable Energy Laboratory, which is in the exact same town as my university, like 2 miles apart. So I have a lot of PhD students that actually go to the national lab for their research. So this was a really fascinating article, a study of a microgrid using solar plus battery plus hydrogen fuel cell north of the Arctic Circle in this town. I'm not even going to try and pronounce it. What did you say the name of the town was? Kotzebue. Okay, Kotzebue, Alaska. Population.
It's a big, I don't know the exact population, but it's a hub. It's
Okay.
About 7,000.
7,000. All right. Yeah. So the idea here is, most of these remote communities run on diesel powers. Diesel is already expensive, and now when you have to transport it to crazy far places that are locked in by snow 7 months of the year, that adds even more to the cost of diesel, right? So if we can do something locally, even if it's expensive, it may make sense. So that's where these kind of solar plus battery plus fuel cell type microgrids start to look attractive. And so they did a study looking at this for this particular community. Here's the basic scheme. So you have renewables, solar and wind, and you can charge batteries, and that's good for kind of short-term storage, like 4-hour kind of things. But that's not good enough for like long-term storage, like in the depths of winter, or if you have a week with a blizzard, a ground blizzard that wipes out all your solar. And so, can we then add one of these reversible fuel cells that I was telling you about that you can run backwards and forwards? You run it in electrolyzer mode and make hydrogen and store it, and then run it in fuel cell mode to make electricity. You can go back and forth. So it's like a giant gas battery, but it can store effectively for days or weeks, whereas the normal battery can only store for a few hours, right? So maybe we can hybridize these two types of storage, and that'll now give us a better coverage of the year. Okay, and so a couple of kind of conclusions that in fact, going to a renewables-based microgrid actually lowers costs compared to diesel only. And the sweet spot is about 50 to 75% renewables. So you still then would use diesel to cover the gaps, the other 50% or 25%. Now, if you want to get rid of diesel almost completely, you want to go above 75% renewables, then you definitely need to have the hydrogen and fuel cells. That's the most cost-effective solution. Just adding more batteries isn't going to get you there, or it's not going to get you there cheaply. So this is where hydrogen and fuel cells come in. The other advantage is it can dramatically improve resilience. Fuel cells can act as a grid inertia provider better than batteries can. So sometimes these microgrids really struggle with inertia problems, where kind of the fluctuating loads, either from demand or supply, are messing with you, and you need something to kind of buffer that. Fuel cells are really good at that. And they also protect against diesel prices, right? So this is a sensitivity analysis. This is super fascinating. And so these are what are called tornado charts. So they say, like, here's the current cost of this microgrid. And then let's vary one parameter and see the impact on the cost of the microgrid, right? So if we make one parameter better, cheaper, that's going to be the blue, right? How much of an impact is that going to have on reducing costs? And if we make it worse or more expensive, how much of an impact is that going to have on making the cost more expensive? And so you kind of get a tornado shape here, and you rank these parameters from most important, most sensitive, to least important, least sensitive to total cost, right? So the wind turbine, how much it costs, matters the most. But after that, the thing that matters second most is the diesel price. Kind of makes sense, right? And here they were doing a sensitivity analysis where the base case was $3 per gallon. What is it right now? 6, 7? And that's here in Anchorage?
I didn't check this morning.
6? Right, and that's here in Anchorage, right? So now you transport it up to some remote community, you're probably $8, $9.
Well, they already paid for their diesel from last season.
Yeah.
But when they get new diesel this season,
Yeah,
they're gonna be paying probably $9 to
Right.
$10 a gallon.
yeah. So on this sensitivity analysis here, that second bar, and this was, they were just assuming if diesel got as cheap as $1.60, right, that would dramatically lower cost. As it got as expensive as $4.90, you're here, we're over here, right? We're not even on that chart. Okay, so that's, right, so you switch from diesel to the hydrogen, and you completely eliminate this risk. Okay, now hydrogen has its own risks, right? So they looked at those. Okay, so what if our fuel cell unit ended up costing more? Or what if the hydrogen storage was more expensive, right? And so here they looked at plus or minus 50% changes to the fuel cell aspects. And, relative to the impact of the wind and the diesel price, you see far less sensitivity, right? So the risk of the diesel price swings are much larger than the risk of what might happen with the fuel cell. Conclusion is, may make sense to go to the hybrid system, including the fuel cell.
So propane stores as liquid at relatively at regular temperatures. I don't think hydrogen does.
Right.
So
Yeah,
just thinking of how big of a hydrogen tank do I have to have?
yeah. So, and I don't know exactly what they use here. I think they assumed a tank, storing it in a tank as opposed to some type of like underground storage. That does add cost. That's being factored in here. So it's not a huge impact, but yes, it's important. And that's where maybe going to a liquid fuel propane. Now that's going to reduce the efficiency of your fuel cell, so that's a trade-off. It's also going to reduce the lifetime of your fuel cell because they're not going to run as long on propane as hydrogen. It gums up the fuel cell over time. We can talk about that actually in a second. Ammonia is a really interesting one. And it probably gets cold enough that the ammonia will liquefy for free without even having to pressurize it up there certain times a year. So liquid ammonia, I would say, would be maybe even more interesting than propane if you can get it to work. Yeah.
What's the BES, the battery?
Yeah, that's the battery energy storage system. Yep. So you can see, and there again, it's $500 per kilowatt hour is the baseline, and then plus or minus 50%. So 250 versus 750. Variation there. If you're interested in this paper, right? That's a little small here, but just take a picture of this. You can look up that reference. It's a brand new paper, 2025, just came out. Okay. Yeah, so this is the sensitivity. Diesel much more sensitive than the hydrogen system. And then, yeah, and so the other thing that was interesting is the authors noted that they didn't consider heat recovery. Remember we said that these fuel cells do generate heat. And if you care about that heat, capture that heat, that can be an added value. And again, for these kind of communities up in the north, that heat is valuable. So that could further improve the economics. You're going to get the heat in the fuel cell. You won't really get that with the battery system. Okay. So other Alaska communities are now exploring these kind of systems based on this. And specifically, I was able to find preliminary studies going on in these places. And I did Google Maps. I know I've been here down in the south, but I had no idea where these three places were, but now I do. Kind of interesting. This one's way up in the north slope, and these are kind of on remote edges of the coast or islands. Are you familiar with all these places?
Helsinki is Kodiak.
Okay, Kodiak.
Dillingham, we southwest.
Yeah.
Wainwright's northwest.
Right. Yeah. Cool. So I got my Alaska geography lesson, but we're looking at this. Kind of fun. Okay. So for the solid oxide fuel cells, this is kind of my main focus. Again, stationary and backup power applications. We look at California, which has had some of the most supportive tax incentives for fuel cells. They're all over. So fuel cells are being used in all these kind of applications. Wastewater plants, you actually get methane from the wastewater plant, right? It generates methane whenever, anytime you drive by a wastewater plant, you smell it, right? So you can use that, right? So it's free fuel. Hotels, food processing, breweries, universities, hospitals, grocery stores, some grocery stores, and then the big one. The big one now is data centers. And data centers are starting to adopt these fuel cell power servers from Bloom like hotcakes. So Bloom has already sold out through 2030 for the next 4 years. They have backlog on these things, and it's all driven by data center demand. So here's some examples. This is an installation at eBay, right? If the eBay system goes down for a minute, right, they print money. So they're losing millions of dollars every minute that their system is down. So they have these Bloom servers, which have basically 100% reliability. Google has these for backup. Caltech, University down in Pasadena. Walmart's, so even you would know, you would never know. You go park at this Walmart, you have no idea what those are. Yeah, so stationary applications. This is the big one for fuel cells, in my opinion. And again, the biggest problem here is in the last red part here, efficient use on hydrocarbons. So that's where my research comes in. I don't know, we still have just a couple minutes left. Looks like just a few.
Yep.
All right. So,
I'm
yes.
sorry, quick question
Yeah.
before you,
Mhm.
so, an application like eBay, their fuel is ostensibly just natural gas
Yeah.
from the local distribution?
Yep, exactly, yep. Okay, so the type of fuel cell I work on is a ceramic fuel cell, but it's a very special kind of ceramic fuel cell. It's only been kind of developed in the last 15 years. They're called protonic ceramic fuel cells. So basic idea of these is they're great for reversible. So you can use them to make power, but you can also run them backwards. You can make hydrogen, but you can actually make more complicated things with them. We're going to talk about that for a minute. So with protonic ceramics, we can actually move reversibly back and forth between the world of electrons and electricity and the world of chemistry and chemicals. And I'm going to share with you just a couple of vignettes. So if you were to peer inside one of these protonic ceramic fuel cells, this is what they look like in a 3D kind of drawing. Here's our fuel, so hydrogen or natural gas coming in, and the air coming in on the other side, protons going across. And these are really good for not hydrogen, for more complicated fuels like methane or natural gas. And that's because on the anode side, the fuel side, you have these tiny little nickel particles on this special kind of ceramic, which has unique surface chemistry with these surface hydrogen and hydroxide type species that help basically reform that fuel and keep it from cooking. So if we think about the two main types of fuel cells I told you about, right? Polymers, low temperature, solid oxide, glowing red hot, red temperature, right? So the polymer fuel cells, the ingredients, that ink, really expensive. For the solid oxide fuel cells, it's the stacked system, all the packaging components. They have to withstand those really high temperatures. So that's expensive. So either way, you kind of get screwed. One thing or another is expensive. These protonic ceramic fuel cells are in the middle region where we like to say everybody's happy. Okay. So we also talked about the other problem with the ceramic fuel cells is the processing, right? Super complicated, takes a lot of time. That makes them more expensive. So we've been working on this problem. We figured out a way to basically take all these complicated steps and convert it into a single step process, just like you would bake a cake or a cookie at home. So if you can make fuel cells like you make cookies, they'll be way cheaper. That's our grand vision. So the other great thing about these is they're omnivorous. They'll basically chew up any fuel. So this is a single little button fuel cell device in our lab without changing anything, without changing the catalyst, without changing how we wired it up. We took that one little cell and we sequentially ran it on hydrogen. So here's the power density curve for hydrogen, right? Obviously, the higher this parabola goes, the better, right? So best performance on hydrogen, as you would guess. But ammonia, not much worse. Don't take much of a hit. You run on ammonia, which is why I was saying ammonia would be a very interesting fuel. Methanol, right? Another liquid fuel. Again, not too bad. But if you wanted to do something more complicated, propane's down here, so you do take a hit. Natural gas, again, a little bit lower, but they can run with sulfur in the natural gas. That's huge. So without versus with, not much of a difference. Ethanol, methane, isooctane, which would be a surrogate for gasoline. You can even run it basically on gasoline.
So with isooctane being, gasoline being lowest, I mean, just, you would expect like diesel or other heavy fuels would probably be similar.
Even lower, yeah. And with those, you might want to do like a pre-processing, reform them before, and then send the kind of simpler reformed fuel species into the fuel cell. Don't let it see the diesel directly or it'll die.
You guys were able, you just sequentially,
Yeah.
you would just splice it first, like with anything, or,
Yeah, I don't remember the exact like sequence.
but you didn't change anything, you just pumped the fuel in there, then the next fuel, the next
Yep.
one?
Yep. And furthermore, we wanted to set, like, this is easy, right? You can just test it on a fuel in an hour or something and then switch it into the fuel. But like, if you tried to run it for days, is it still gonna, we talked about how the performance dies right over time. This is a fun video. So we take high school students into the lab to do these kind of outreach tours. I designed what I call an air breathing fuel cell. So this is one of my protonic ceramic fuel cells. It's the size of a US dime, to give you perspective. And what we've done is we've just taken a dab of silver paste and used that to attach these lead wires to the two terminals, the plus and minus sides of our dime-sized fuel cell. And we've connected that to a little DC motor that's going to power this fan. So you're going to be able to visually see the electricity production. This is what we call an open air fuel cell. So it's the simplest possible fuel cell design. So the top is going to be breathing in oxygen from the air. That's the cathode. And on the bottom, we're supplying hydrocarbon fuel species and heat from a little butane lighter. This is the exact same type of lighter you use for your 4th of July barbecue. All right. So we run this demo live with students. It's super fun. So you hold the lighter there for just a few seconds, right? And then, boom, starts to produce power. You take it away. There's a lag. And then you can do this back and forth and back and forth. Right, so that's the promise. That's how simple and elegant these things can be. Obviously, this is not going to be a very efficient fuel cell, but fine. It's good for visual purposes. Now, the other thing that this shows you, if you got good eyes, you can kind of see the silver wire. It's not silver here anymore, is it? It's black. What is that? When you go camping, you're cooking over a campfire with your aluminum pot, right? What happens to that aluminum pot? It gets all coked up. So that happens when you run fuel cells on hydrocarbon fuels, just like a campfire. So for most fuel cells, that's a big problem. That coke will basically gum up the fuel cell and cause it to stop working. For these kind of fuel cells, it doesn't. So this is a huge advantage. And in fact, we prove this by going to the lab and running these fuel cells on various types of hydrocarbon fuels or alcohol fuels for thousands of hours. So this is basically 1 year. So we ran it on, what is this, C4H10? That's butane, I think, butane. And then we switched it to propane. Yeah, so we did butane and propane for a year, methanol for a year. This was isooctane. So that's the one that gives us problems. You can kind of see the performance starts to drop. This is the voltage. We're drawing like a constant amount of current from the fuel cell, and we're just watching how the voltage drops over time. But yeah, we were able to get a couple thousand hours out of isooctane. Here we did an experiment where we purposely added sulfur contamination into natural gas, and it didn't really affect it. Sulfur will kill almost any other fuel cell, so that was huge. Yeah.
Does it matter if your load is not constant current or a constant
Yeah,
load?
so there's all sorts of, there's many things you can explore about that. So this was the simplest kind of test where we just did a constant load. But yes, you can look at different steps. Interestingly enough, we talked about the reversible cells where you go to electrolysis mode. That is actually protective to lifetime. So if you switch the fuel cell's polarity and run it in reverse, it'll kind of eat away some of these species, oxidize them, get rid of them, and clean the fuel cell. So by switching back and forth and running it backwards sometimes, you can actually extend the life of your device, which is really fascinating. So why does this work? Well, this is something we're still exploring. It's all this chemistry stuff, so I'm not going to bore you with the details, but basically there's interesting surface chemistry associated with these ceramics. And you get these hydroxide type species that will eat the carbon, the soot that tries to deposit, and the sulfur, and oxidize it to SO2 or CO or CO2, which will leave. Right, so you basically can clean any solid deposits that start to build up. So we can run them in reverse. Talked about that. Here's actual data from the lab. So here's what we're doing is we run it as an electrolyzer. So we're charging a tank, we're filling a tank with hydrogen, and then we can switch and discharge. Now discharge mode, we're producing power. And then we can go back to charge, back to discharge, back to charge. And we do this over and over again. And each time that we do one of these cycles, charge, discharge cycle, we measure how much hydrogen we're making, how much power we're producing, and we calculate the round trip efficiency, right? And so these data points up at the top, those are the round trip efficiency that we've calculated for each charge discharge cycle. And we did this 30 times over the course of about 80 hours. And you can see that it's pretty stable, a little bit of a drop off, but the round trip efficiency is on the order of 76 to 74%. So batteries actually aren't that much more efficient. You don't really notice this, but like when you charge a battery, you waste some of the electricity that you're using to charge the battery. It's not 100% efficient charging it. So you may waste 10% of your electricity as you're charging it. And then when you turn around and discharge your battery, again, it's not 100% efficient. So you may waste 5–10%. So when you like do the same kind of calculation for a battery, you're going to be on the order of 80%. So this round trip fuel cell, not much worse than a battery. We talked about ammonia. So we've actually done this with ammonia. This was really interesting. So same thing, reversible fuel cell, power generation mode, make electricity, ammonia synthesis mode. So here, instead of making hydrogen, we're using the fuel cell. We're taking pure nitrogen, and then we are splitting water to make hydrogen, and then reacting the nitrogen and the hydrogen to make ammonia inside the device. So it's same thing. So we're cycling here between ammonia synthesis mode and ammonia fuel cell mode, back and forth, back and forth. And we've tried this even more complicated with a reversible natural gas or methane fuel cell. So here, again, you're supplying methane and water to one side of the fuel cell, air to the other. This will produce power, just a methane powered fuel cell. But you can flip it around. And in this case, you need to provide it with CO2 on one side and water on the other side. And you can actually make, through these different kind of chemical and electrochemical reactions, you get a cascade of reactions. Eventually, if you do this right, you design it right, you're at the right temperature, you can actually make green methane. And you can go back and forth. All right, so that's basically how these protonic ceramics can transform reversibly between the world of electricity and the world of chemistry. That does it. So thank you for your attention. I'm happy to answer any other questions you might have.
So I'm intrigued with the question in general, just the efficiency, and the one you showed, the support stuff that takes to run the whole system.
Yeah.
How much is the parasitic loss?
Yes, excellent question. Yes, it depends on lots of different things. So I can't give you just a single answer, but you're absolutely right to be concerned about that. So if we measure what we call the cell level efficiency, that can be really high. That can be 80%. But now when you add all the system components, you're absolutely going to take a hit. So really well-designed fuel cell system, if it's these kind of high temperature ceramic-based fuel cells, you can still get to 60% electric power efficiency, even 65%. And if you care about the heat, so you have combined heat and power, you can get to 90%, 85 to 90% without trying too hard, 85 to 90% total combined heat and power efficiency.
So you use the example of hot water heat in Japan.
Yeah.
I have, that just boggles my mind. How does that make sense?
What do you mean?
How does it work? I mean, what's the, in my house, I make heat with natural gas and it warms my water. And you know, the inefficiency is just in the burning the fuel.
Right.
So how does the fuel cell make that better?
So you don't have to, so you can pick the operating point of your device based on how much you value the heat versus how much you value the electricity, right? So you don't have to operate at maximum efficiency point where you're getting most electricity and a little bit of heat. You could choose to operate it less efficiently, where you're actually getting more waste heat. If you value that heat. Yeah, absolutely. So of course you're going to need more total natural gas fuel if you're going to be heating all your hot water for your house and producing electricity, right? There's no free lunch. But overall, you're still going to be more efficient than if you had grid electricity plus your water heater running on natural gas. Yeah, that's the idea.
My water heater doesn't make any electricity.
Yeah, most people's don't.
In fact, it uses electricity.
Are there any ship-based applications?
There are some, yeah, I'm less
Like
familiar with this.
LNG tankers seems,
Yeah,
like if it's scalable to
Yeah.
megawatts.
yeah,
Right, and you're on a ship that's carrying a bazillion.
yeah.
LNG tankers already use the LNG, it's on there, it's the power of most of it. So. but-
The one that I've heard most about is the ammonia for ships. I don't know why, but the idea is using ammonia as a bunker fuel for marine applications. And then you could use it, you can actually retrofit diesel engines to run on ammonia. We have to do an ammonia hydrogen blend, they won't run on pure ammonia. But there's a certain ratio of ammonia to hydrogen that to a diesel engine behaves the same as diesel. It's really cool. So if you can get that ratio right, you can use with very little modification existing diesel engines on these hydrogen ammonia blends. So now you can go to ammonia bunker fuel and you can actually, so you could have for the propulsive transport of the ship, you probably still have engine, but for the ancillary like electric loads on the ship, for the captain's quarters and lights and all that kind of stuff, you have a little ammonia powered fuel cell. Yeah.
One other question, I'm intrigued by the idea of a fuel cell being a good source of inertia for power system. Again, that just seems, in my mind, inertia comes from spinning mass.
Yeah, so I think it's because of there's a lot of phase lag in the fuel cell. There's sources of inertia from kind of a thermal and electrical kind of response. So like a battery will respond super fast, millisecond kind of thing. So it's actually good for like frequency modulation. Fuel cells won't respond that fast, they're slower. So they're kind of a minute time scale, which is good actually. It becomes an asset for the grid to have that slightly slower responding system basically to provide the inertia. I'm again not the expert on that part, but it was pointed out in Aaron's paper as an important bonus of the fuel cells.
Cool. What were the size of all those units, the backup units that all those AI or the
So the standard
Google
Bluebot
one, yeah.
energy service a few years ago was 200 kilowatts. I think now they've gone to bigger units.
500 kilowatts?
Say again?
Like 500 kilowatts?
Yeah, I don't know. And I think they even sell megawatt size ones. And of course, you can just buy a bunch of these, like we saw with the Walmart run I just had. Right, so
Those
I don't
are
know
mostly
what
from
the
Bloom Energy or?
Bloom Energy, they're based in California. Yep.
Better get on the wait list.
And which of the technologies could they use?
They use the high temperature solid oxide. Yep. So it can chew up the natural gas fuel directly.
How big are your proton ceramic? How big have you gotten those up?
Yeah, so most of our lab testing is button cells, so they're little, we either do cells that are about the size of a US quarter, or we have a little bit larger one that's about the size of a US silver dollar. We've gone to kind of 5 by 5, so 25 square centimeter cells. And then we had one DOE funded project with an industrial sponsor, with an industrial partner that makes fuel cells for a living. They're a commercial fuel cell developer. And so they made larger kind of 100 square centimeter protonic ceramic fuel cells, the largest protonic ceramic fuel cell anyone's ever made. Fortunately, we haven't published this yet because of all the industrial side of things. And then they also made the world's first protonic ceramic stack. So remember we talked about stacking? So they were able to successfully stack up 10 of those big old plates, 100 square centimeters each, to stack. And we got to, I don't remember how much total power, something close to a couple hundred watts, maybe even more, maybe close to a kilowatt.
Okay.
Yeah.
So that'd be like kind of a kilowatt battery.
What's that?
I think that'd be like the equivalent to like a portable battery you're gonna take around from
Yeah,
that kind of size.
right. Yeah. Cool. I'll come down to Colorado sometime and visit. We'll show you the lab.
And the password for today's online survey is flexible, all lowercase.
All right.
Thank you very much.
Yeah, thank you.
That was really interesting.
Awesome.
Great.
Hey.
Thank